SolidCAM Milturn webinar. My name is Florin Eugene, and I will present you today some new options, new developments in and also the old ones, but improved in our Milturn module. So I will start with a small list of issues. We will talk about machine ID, and we talk about STL tool mounting and STL holders. We talk about tool table, how to use STL holders defined in STL library, how to mount the tools, the directions, our options, and setup. Setup is a very important part of CAM part definition, and about some new operations, and the final issue is the machine simulation. So we'll start with the machine ID. The machine ID was developed in order to support and to give to the user the option to control the machine. So if we want to control the machine, the entire machine, any option, any device, so we need to know the machine. We need to describe the machine. When I talk about a machine and a description, I talk about devices like the spindle and the table, axis for each device, and options. All of the attributes, all the options that we will describe in this file, in this machine ID definition, will have influence on CAM part definition, in machine simulation, G-code, in also in our possibility to control devices in machine control operation. Any option that I will define in machine ID, I will be able to control it in this operation, MCO. For machines and parts from earlier versions, this machine ID file will be created automatically and also manually. We'll go to here. What we need here, what we need to describe, is any mechanical device that can move or can make a specific action in the machine. We need to define it. The device is, for example, the table, and we can see here examples of device. This is the table, the support of the tilting axis and the rotary axis. For the back spindle also we have the support of back spindle with two rotary axes. In general we have turret, we have table, and any other form device that standard we have, like a tailstock and a lunette device or a bar feeder, but we are ready to support any unknown, any not predefined device in the machine. What is the difference between the type of devices? The turret is the device that holds the tool. It's for tool holding. The table will always hold the part. It's part fixing. The bar feeder is for raw material holding and inserting into the machine between the parts. Part catcher will collect the ready machined parts. Tailstock and steady rest they are devices to support the part in the time of machining. Form device, as I said, for all not predefined devices. Now, I will not entering in details for how we define and how it's another session about specific on VMID. Today we have several issues to talk. So the machine ID file is in the country under the CAM part, and we can the user can open it in read-only, or he can also uncheck this checkbox and to change it, to add some devices, add some new options. I will go straight to submachines, because in machine ID we will define a device like spindle and table, and we'll define first of all we define the machine with options of the controller. The second we define devices, and the third step is submachine definition. A submachine is a combination of one turret and one table. We have here an example of 4 defined submachines. Upper turret on the main spindle and lower turret with back spindle. Also we have a lower turret with main spindle and upper turret with back spindle. We have 4 submachines, 4 small machines in one complex machine, and each one of them can work independent. When I say independent, I mean this turret can work on main spindle, and in the same time the lower turret can work on back spindle. What connects between them, between the machine, is the synchronization. Also, we will talk about this in this webinar. So, not to enter in details and how to define the VMID file, this machine ID, it's meant to give us a complete description of the machine and capabilities in order to control the machine in operations and in machine control operation. The machine control operation is our tool to use attributes and the options predefined in machine ID. For example, I'm opening a new machine control, and we just drag and drop the machine. If I define in the machine ID that this machine, this control have a machine stop or optional stop, now I can operate him on and off. I can activate it, I can deactivate it, and dwell all kinds of floods and air, bed rinsing, chip conveyor, any activity on the machine controlled by the machine controller. We also can control this activity here, this action here in the machine control. Now, for devices, we define axis. We can move the device to specific positions in the machine between the operations, before the operation. We can rotate the spindle, activate coolants. We can change a tool. We can measure a tool if it's defined that this machine have a measuring tool device. Complete control on any device on this machine. For table, the same. In turning, I can check the torque. I can change pallets on the machine with many pallets. Spindle orientation, to orient the tool in the spindle. Working mode. In a mill turn machine, our table spindle can work in a turning mode or a milling mode. That means the C-axis, the fourth axis is connected. Any of these options operated here will get a special M code, G code, or some kind of command in the CNC program, in the G code program. Movements, we will always see for each device all axes. As for the table one, if I want to move, I will see only axis C on table 1, C table 1. But if I'm going to a turret 1, it's upper turret movement here. Sorry. I will see X, Y, and Z axis. I can make this movement part related. That means from our present coordinate system, or machine related, from machine coordinate system. In the user language, use G54 up to G59 here, part related, and machine coordinate system use G53, for example, with rapid or with feed. Submachine also can be controlled. We can output an interpolated movement for a submachine for all axes of all existing axes in this submachine. This submachine is a combination of turret 1 and table 1, axis related to turret 1 and axis related to table 1. They are all here, and I can move them also with rapid and feed. This is machine control operation. We use it for to activate all kinds of coolant, spindle rotation modes, like as transfer, milling, turning, for movement to safe position, to change the tool. It's a very important tool in a mill turn. Yes. Improvements that we do in CAM part definition for stock and for target. All options to define the stock from as a cylinder, a box, a revolved boundary around Z. That means you draw a sketch and it will be revolved around Z-axis. Extruded boundary, 3D model, and STL. A previous remain stock from a previous part, you can use it, import here this STL, and use it to continue the next level, the next machining program of this part. Okay, let's go to SolidCAM STL library. The standard milling tools, they are always some kind of revolved form, and we can use the all the SolidCAM options, drawing, sketch, or building holders with all the options, or we can download directly from a tool manufacturer the 3D model. So this is an STL. We can download all kinds of formats like XT, Parasolid, Step, STP, SAT, ASYS, import in SolidWorks, export to STL, and import the 3D model here in our table. In the moment that we import, we just have to define two things. One is holder mounting point. That means where this holder, which point will be mounted on the station, on our turret, which point. So this is the red point here. You see a difference from the red and blue point. And tool mounting point, where the tool will be mounted on this STL here. X, Y, and Z position for each one of them. Not always the model that you will import from any website, any a tool manufacturer will not be always in the correct position. So SolidCAM can control and bring this point tool mounting in the correct position. I can move it on the Z-axis, on Y, and on X. This point will be mounted on our station. Let's reset them. And as I say, the tool will be mounted in the blue point, on tool mounting point. Now, this is related to milling holders, STL holders. All kind of types, HSK, ER, Capto. We have with different types of Capto, C5, C8, C4. Any one of them, just import, define the tool mounting point, it's ready to work. Shrink in. I have here a lot of examples. I have also a quill, a tailstock defined. I can mount this tailstock on a rotary table, for example, and I will use the rotary table as a support device. Now, you're going to turning holders. Here, we really get the advantage of STL holder, because none of them, they are not a revolved form, a revolved sketch. They're always complex and complicated 3D forms. We will only insert here the insert of the tool, in this position. Blue point is defined as tool mounting point. That means our insert will be mounted here. Internal tools. I have a lot of examples for different kind of inserts, 55 degrees, 35 degrees inserts. A combination of STL holder with shank. Also, the shank can be downloaded from the website and you will mount only the insert. Good for machine simulation, good for collision check. Holder, spatial holder design and only for insert usage. So those are our capabilities to define any 3D model as STL. In the moment that you define import in here in this table, you define mounting point and tool mounting point. Now we can use them in our tool table. In my tool table, I will add a new tool, and I'm going to holder, global STL holders, and just search for one that I need. Now, I have this tool and I have this holder. Yes. Very quickly, I will define that this tool is, go back to topology, is a right. Yes, it's a right. And I want it with insert in this way, going to 45 degrees, reset the tooltip position. It's already in place. Now the topology, the IC diameter will be 12.7 and 476. Shank is not 90 degrees. The shank will be type G, no, 95 degrees, yes. And check here, insert only, the shank will disappear. And I have only the tool, only the insert mounted on STL holder. Save this tool in save tool tables and use it every time. Just import this tool. I have a tool table already defined, mill turn tools with composite tools, with holder mounted this composite tool mounted on STL holders, any kind of insert like W, left or right, C type, left or right, 55 degrees D type, left, right, all tools with all positions, all types, left and right, defined with STL holder, grooving, threading tools. All the time I have left and right. The same tools now mounted on the different STL holder, on the 45 degrees STL holder. I spent a few hours to define, but now you don't have to do anything, just import. Import this tool. Okay, I have the tool here. I can work with this tool now very quickly. This is about using STL holders and the new composite tools. No, don't save. Now, when we start to program a part, the user on the machine is fixing the part on the table, and he will measure the home position with a probing device like Renishaw or any other type. He is going to define where is the coordinate system on the part. Now the same, he called it setup. The same we need to do in SolidCAM. I need to tell to our machine simulation where is my part mounted, placed on in the machine workspace. So, submachine, turret and table are connected and work on Mach 1 position 1. This is my coordinate system. And I have a clamping device, this fixture. There are 3 jaws. There are 272 millimeters distance from table, from submachine. Red point, it's showing me where is the face of the spindle. Define it in machine definition. I define where is a submachine coordinate system for turret 1, table 1 in machine definition. Now I define where is the part connected to this submachine. Here is the place. This machine, we start with a simple one. I have a large database of different kinematics today, and I will start with 1 rotary turret and 1 table. It is already running. Just a second. Yes. So I will define a schematic machine simulation for any type of our supported kinematics. But maybe before that, I will present you what we can do. Today we can support machine like NTX 1000. This machine, we have it in our technology center in Germany. Upper turret with B-axis, and lower it's a rotary turret, and the back spindle with additional B-axis around Y. Other machine that we can support, it's one of the examples that I have all the 3D models. A DMU 80 Evo linear. This is a milling machine with turning capabilities. That's a table with 4th and 5th axis on 45 degrees, and this machine can turn. And I will show you also on this machine how we can work on the face of the part and to rotate the ZX plane around the axis. Other example is Integrex. We all already know. We talk about Okuma, Macturn with B-axis type and rotary turret, 2 tables. We talk about Multrus, 2 tables and B-axis. Here we have also a part catcher. Yes, and we can command this part catcher with our MCO. We finish an operation, maybe we need to cut now, we will do a cutting operation, and the part will fall down into the part catcher, and the part catcher will collect the part. And Nakamura Tome, it's a standard 2 rotary, 2 tables, but our presentation I will present on schematic machines will be more faster, and we can see we don't have the entire machine housing around the part, and we can see more clear about the operations. On a simple machine like this with one rotary turret and one table, the user wants to finish the part in one program. So our option is the setup. Define the setup. I define first coordinate system on this side of the part with jaws. This is the fixture in the setup. I'll make the operations, turning, milling, what I have to do. Now the user will pull out the part, rotate 180 degrees around X, and change the jaws on the spindle, and continue to work on the back side of the part. So our setup solves the problem. Now I will define another coordinate system on the back side of the part, Mach 2 position 1, with the same submachine. I define a different clamping fixture, the different jaws, and a different position from the spindle, from the face of the spindle. Now we have 240 millimeters my coordinate system from the face of the spindle. And he can continue to work in the same program, on the same part. He will finish operations on front and back of the part. Now let's see a schematic very quickly. Machine simulation. We're going to more complex parts, but also those simple options, they are very useful for the user when you don't have a very complex machine but you still want the solution. We develop them. Rotary turret and all the STL all the tools defined with STL holders. We can see them here. Check collisions, check the tool path. I will go very quickly on the turning example, and I have now a milling example. If you have y-axis on the turret, so you can work x, y. Now the next example of operation is if you don't have a y, you need to work x, z, and c axis. The same on a radial OD operation with fourth axis. Drilling, radial drilling, and here I have an example, but I don't have the exact holder, STL holder. I just wanted to show that we can we have the option to we support angular heads on rotary turret. That means if I have an angular head with the angle, the tool can be mounted on a specific angle. We support this kind of operation. I just don't have the correct STL. I'm still searching for an angular head 3D model, but the tool is defined in 45 degrees, and we can use the rotary turret to work on an angle plane. Now, let's see what's happened. I define the setup now, and the user pull out the part, rotating 180 degrees, change the fixture, and continue to work. and the same program. Very simple and very easy to set up. The same examples of working with XY and XZC axis. This for a simple machine. Now let's go to another example, and I will take one spindle turret, one rotary, two tables. Example number 6. Again, yes, I have it open in my second screen. I'm working with two screens I forgot about. Yes, close it. And this kinematic is the same as we see the NTX machine with additional B-axis on back spindle. Back spindle can rotate from 0 up to 225 degrees. Now, on this machine, we'll see an example how to work with the back spindle in a different position. Yes, all tools they're all mounted, and for the spindle turret and for rotary turret. Fixture is in place as we define in the setup, and also the fixture for the back spindle is already in place. Here we have an example of a balance roughing operation. We'll go and I will have a short description, explanation of this operation. Working with two tools on the same geometry in order to remove the material faster. Operation, the toolpath is synchronized. Start of operation synchronized, the start spindle, everything should be synchronized in the program. Some 5-axis examples of working with 4-axis and without. Let's go to part transfer. I'm going very quickly forward. After operation with lower turret, the MCO will help me to define a retract to a safe position. Retract on X, Y, and Z. I'm on reference. Back spindle is coming and catch the part. Retract to the reference position, and we can continue to work. Also, I define a balance rough operation to remove faster the material, the stock. A retract of lower turret and continue to work with upper. Let's see, I want to go to see working operations on back spindle with an angle. Working on back side of the part when back spindle is in 30 degrees. For our NTX machine is very useful option because we have a small space. Working on 0 degrees on parallel to z-axis, the upper turret can have a collision with the main spindle. With this option, work on angle, we eliminate any danger of collision. Yeah, another option is working on side, on position. Even if I'm positioning the B-axis to 90 degrees, and I can continue to do milling on the side on position. It is possible also. Another example of a spatial support that we add in SolidCAM 2013 is machine, let's see, I think it's 4 or 5, no, 1 spindle, 1 turret, 1 spindle turret, 1 table. Let's see, 3. This is the DMU similar kinematic with table on 45 degrees. And here I want to show you the new option that when we have, let's open the machine simulation to have it. Yes. When we work with B angle on 0 degrees, that means we will work on the face of the part, turning on face. I can rotate the tooling spindle and work from any direction. I can work on X direction, ZX plane. I can work on YZ plane, minus X and Z, minus Y and Z. 360 degrees around Z-axis. That's what we have. That is what we have here, the spindle orientation. When our tool direction is parallel to turning direction, I will have this field open. When the B angle, additional angle of tilting, is not 0, spindle orientation is cancelled automatic. So the first operation is a face, and after that I will rotate it 90 degrees, 180, 270. Tool, spin orientation 270. That's what I expect to see in machine simulation. Okay, so the first operation in ZX plane, rough and finish. Now you see tool in spindle rotated 90 degrees, and the tool pass will be here. Show me the tool pass. I'm working on YZ plane. I'm working on other side of negative X. 360 degrees around. No problem. Also, I can work with B-axis tilted 90 degrees, long, rough turning. Now go fast. And on any different angle is not 90 degrees. We have now, let's see, 96 point something. Yeah. It depends. It's a calculated angle. When I define in the job, we are here. I define that the tool will work 50 degrees deviation, additional angle. For the 45 degrees axis in machine will be calculated to the spatial angle, like we see. Everything else is the same 5-axis. Let's see. Simultaneous 5-axis and position, milling operation, drilling operation, the standard things. I will go to drill on different position, and machine control for the end go to a safe position. Also can be used, even if you have only one turret, one table, MCO can be used for any kind of activity. Now I will go back to a part on an Integrax machine to talk about synchronization. Turret synchronization, user interface is from right-click on operations, and we get it here. Now, we have the option to define that this machine will always work synchronized. There is no other option. This machine should get the G-code always synchronized. So in the CAM part, not here, in the settings, turret synchronization, mode auto synchronization as in country order. You will always get the G-code, the program, and the simulation synchronized as in country order, automatic. But you always can change it. The user can always delete some synchronization and or add synchronization. That means from the country, from this order that we have here, the part is already synchronized. I can generate the G-code, send to the machine, and work. But if I want to optimize the part and see this drill can work when on upper turret, yes, can work when on lower turret. If I have a milling operation, let's take this drill with this milling, they can work together. There's nothing interfere when they can work on the same table even. The proper angle is used, so I have no problem to do it. Okay, delete the active synchronization and add one. Not, this is a drilling, a turning drill. No, I have the turning operation. I need a milling operation. So let's take two turning operations. is a turning. I don't have it here. Don't have any turning operation on. It's only balance roughing, but this drill delete all synchronization. I would just want to give you the example of how to synchronize them. Let's synchronize MCO. This MCO and this MCO, they will start together. I have this option, this button, start together, one after another, and end together. So I select with control one operation, MCO on this channel and second on this channel, start together. Now I synchronize them. In order to synchronize milling operation, we have to synchronize milling on this channel with milling on other channel. I cannot synchronize turning with milling. For turning, my table will rotate. For milling, I don't need the table rotation on the table, so it's impossible. This part, when I create this part, I have several milling operations, and with the lower turret, I have only turning operation. So I cannot synchronize a turning operation with a milling operation. But this is the option that you have. If you have here milling and here milling, working on the same table, select both of the operation with a control and synchronize them start to start, end to end, or one after another, start to end. Delete all. All the time I can go back and synchronize, delete any change, and synchronize by country order with this button. Now we'll say, okay, we synchronize this in all the program here. Now I want to see on the G-code. So we don't have any problem to generate G-code for synchronized turrets, channels. I'm using SimCode just to show you. Here I have the option to show in parallel two different channels. I have the setup on multi-channel and working on upper turret channel is in the left side, and channel 2 is the lower turret in the right side. P command is for synchronization. I have first balance rough operation on the channel 1 synchronized with balance rough operation on channel 2. Right after the balance rough operation, I have the lower turret retract. Exactly what I have here in turret synchronization. Balance rough on upper turret on channel 1 and channel 2. Lower turret retract on channel 2. After the lower turret retract on channel 1, upper turret will continue work from operation number 3 to 9. Exactly what I have here. Lower turret is going to retract. I have another synchronization point, 36. From here, upper turret will work alone on the part, and another synchronization point, the lower turret will work. All the program, main program is synchronized. As you already see, we support subprograms in our post, even in the mill turn. And we synchronize the subprogram. Not only the subprogram, we don't have synchronization only in the main program. Also in Let's make it like this to see from here. I have the subprogram for balance roughing on the upper turret and for lower turret. Inside the operation, every movement, we have synchronization on toolpath. Every start of a step down, every step down that the tool will take on the rough operation, it's synchronized. The start on upper turret and on lower turret, they will start together. We have synchronization points on every step. So synchronization for 2 and 3 turrets we already do. We have machines, we have working machines with a complex synchronization like this. In the future, we'll be able to optimize automatic optimization of times, where we will be able to generate G-code only for specific channel. Have a lot of new implementations, new features that we are working now, and we develop them for the next versions of SolidCAM, next service packs. This is all for today. Thank you all to be here and to be present to participate to our webinar. And we will meet again in the next webinars. Thank you very much.